Study Unit 5, Lecture 1. Study Unit 5 focuses on what are called naturally commutating AC to DC converters. So if this term is broken down, an AC to DC converter is a circuit which converts AC power to DC power, or rather AC current and voltage to DC voltage and current. So there will be some AC source, and it'll go through some converter network which will generate a DC current and DC voltage which will supply power to some load. Commutating is just another way of saying that this network has a switching action which takes place in the conversion process. Finally, the term naturally refers to the fact that these networks in naturally commutating AC to DC converters are passive networks, so there are no switching control schemes or external controllers which determine how commutating takes place. Or more simply put, the nature of the AC signal will cause the commutation to happen naturally, causing a DC output. So a useful way to measure the quality of this conversion process is to look at the ripple factor on the DC current, and this is defined as the AC input divided by the DC output, and can be expressed by the square root of the V squared RMS minus V squared DC divided by the DC voltage squared, which simplifies to FF minus 1, or the square root of FF minus 1, where FF is the form factor of the converting network. So the first circuit that we'll examine in this study unit is the single phase half wave rectifier. In other words, the AC source only has a single phase and is only a half wave rectifier because only half of the AC cycle is used to generate the DC voltage. So the operation of the circle is quite simple. If there is a resistive load, then when the AC voltage starts to increase, it will go above the turn-on voltage of the diode will turn on and conduct, and then there will be some output current. Once the AC voltage starts to go into the negative part of the cycle, this diode will turn off and there will be no current conducting. Once AC signal goes positive again, there will be current again, and it should be fairly obvious that only on the first half of the AC cycle is there actual conduction to the resistive load. So for the single phase case, Vout is defined by the following equation. Vout is a function of omega t, which is frequency, equals the output current, I0, multiplied by the resistive load. The AC signal has two parts. There's a positive part of the cycle and a negative part of the cycle. There will be two states for this output voltage. The first will be root 2 multiplied by Vn multiplied by sine omega t for the first positive part of the cycle, and the output will be 0 for the second part of the cycle because the input is negative. So over a long time, the average DC voltage is going to be the average voltage of these positive pulses, and that can be determined by integrating the voltage function over a full cycle. So this is done over here, and it can be seen that the output voltage is 0.45 times the maximum input voltage. The RMS output voltage is simply the square root of this, and if you take the square root of this integral here and simplify, you simply get 1 over root 2V. The power is a half V squared over R. The AC current present in the load is given by this expression here, and the form factor for the half wave rectifier is pi over 2. It's not too different if there is some back EMF in the load. In the presence of a back EMF, the required voltage before the diode starts to conduct needs to be higher, so this ends up reducing the load current being pushed through the resistor. The total load voltage is now given by a DC offset representing the EMF plus whatever current is flowing through the resistor, which is shown here by the green line. Graphically, it's quite easy to see what the presence of the EMF does to the load current, but it does complicate the math somewhat. So as mentioned, the diode only starts to conduct once the input voltage is higher than the EMF voltage, and this happens at the point alpha, which is simply defined as the arc sine of the EMF voltage divided by square root of 2 multiplied by V, which is just this point here. For an AC signal with frequency 2 pi, conduction stops at pi minus alpha, which is this point over here. So the diode stops conducting when omega t is equal to pi minus alpha. This staggered conduction results in the output equation for the output voltage changing ever so slightly, because now the presence of the EMF source has to be taken into account. So over here is the same expression, or rather the same integral for the output voltage, but the effect of the EMF supply or the EMF source has been taken into account. So now the output voltage is expressed as some DC constant, or rather a function of the EMF, plus the periodic function from the AC source. The total power output is now given by the power delivered to the resistor plus the power delivered from the EMF source. And this can be expressed as the RMS current at the output squared multiplied by the resistance. So that's the resistance flowing through this resistor generating power here, plus the power contribution from the EMF source. Stepping away from the two basic circuits which were shown now, a more realistic case is some half-wave rectifier with an inductive load. This means that there is an inductive and a resistive part, or rather a resistive component, to the load. So this is the same circuit as before. There is some periodic voltage input. There is a diode which will be forming the rectifying. There is an inductive component and then the resistive component. And then the output voltage will be over the inductive and resistive components. Assuming this inductor has no energy stored in it, the load current will start to conduct when the input goes above 0 at 0 degrees. So in other words, the AC source will deliver current to both the inductor and the load, and even though the AC source may have gone below 0, the energy stored in the inductor will still provide current to the resistive load. Of course, the inductor can only store so much energy, and at some point the energy in the inductor will be depleted, and then conduction will stop. And the point at where conduction stops is marked by beta, which is the extinction angle. This extinction angle demarcates where there is no longer conduction to the resistive load. So to understand how the circuit works, Kirchhoff's voltage law can be applied to this loop over here. Simply stated, the voltage across the inductor plus the voltage across the resistive component should equal the total voltage provided by the source, and this is expressed as VR plus VL equals V. Substituting the individual voltage expressions in, we've got the voltage across the inductor LdIdt plus R multiplied by the current through it, so Ri is equal to the total AC source voltage. So solving for the current and applying a lot of trigonometric identities gives the current as a function of omega t over here. The solution for the current requires that omega t be less than the critical angle beta, and also that beta is larger than pi. Z, theta and tan theta are used to represent the actual values of the circuit elements, and I'll just summarize here. The impedance Z is simply R squared plus omega L squared, which is the impedance of the inductive and the resistive component. Tan theta is the quality factor of this inductor, and R is defined as Z cos theta. This extinction angle is determined by the load impedance Z. So the extinction angle is fairly easy to solve for, well, not that easy, but as long as beta is larger than pi, it is simply the solution of this equation where I equals 0 and beta is between pi and 2 pi. Although the substitution is quite simple, the solution of this equation is what's called transcendental, which means that it has to be solved with iterative techniques. Theta is the load impedance power factor angle, and this can be used together with this equation to graphically solve for beta. For a purely resistive load, beta will reduce to pi, and for an inductive load, beta will increase to 2 pi. Two useful criterion to understand when looking at these types of curves for an inductive load are the inductor equal voltage area criterion and the inductor load zero slope criterion. The equal voltage criterion simply states that the area under this part of the voltage curve should equal the area under the second part of the voltage curve. In other words, the energy stored in the inductor must be equal to the energy discharged out of the inductor if beta is less than 2 pi. The slope criterion simply says that when the slope of the current is 0, in other words, is no longer changing, then the voltage across the inductor will start to change. So here is a plot of the current through the inductor, and when the current reaches a maximum and starts to decrease, the change in current here is 0, in other words, the gradient is 0, and this corresponds to a change in the voltage across the inductor. The halfway rectifier shown here, instead of having an inductive load, has a capacitive filter over the resistive load and no inductive element. So to analyze this circuit, we can apply Kirchhoff's current law, which simply says that the supply current Is must be equal to the sum of the capacitor current Ic and the output current I0 or I out. So to express this in terms of the value of the circuit elements, it is simply the current for the capacitor given by C dV out dt plus V out divided by RL. Solving this equation gives I as a function of time as root 2 Vs, which is the amplitude of the source voltage divided by the load resistance, multiplied by the square root of 1 plus omega RLC squared, multiplied by cos omega t minus theta, where theta is arctan of 1 over omega RLC, which is the impedance of this network over here. Following some derivation steps from the reference text, the output voltage is V out of t is root 2 amplitude of supply voltage multiplied by e to minus omega t minus beta multiplied by tan theta times cos theta. And this will describe the output waveform seen here. What all this math really just means is that the capacitor will store some value, some energy, which during the negative parts of the cycle when the diode is not conducting, this capacitor will at a linear rate discharge into resistor RL. So there will be a brief conducting period between conduction angles alpha and beta, which is demarcated as theta in these equations, where there will be conduction through the diode. When the diode stops to conduct, the energy stored in the capacitor will discharge for the period when AC energy is not being delivered to the load, as shown by the green line over here. Until the next cycle, the AC voltage picks up again, there is conduction, the output voltage increases, the capacitor charges, and then there is discharge again. Essentially what the filter capacitor is doing is in the other half-wave rectifiers where there was only conduction during part of the cycle, the capacitor effectively smooths out the voltage peaks to get a more even voltage output. The circuits covered in this lecture focused on half-wave rectifiers where there was only partial conduction during the AC cycle. So for coming back to this example with the RC load, there is only conduction for a small part of the total cycle where the converter network provides energy for the rest of the cycle. The remaining lectures will primarily look at full wave rectifiers for both single and three-phase voltage sources.